Okay, Harvard 3.1. How far did the car go? Take 9 or something. My goodness sakes. Okay, so here we're going to look at a table of data, and we're going to find the distance that a car will travel from 0 to 5 seconds. And it does note that it is traveling at an increasing speed, and I'll note how that comes into play a little bit later, but it's really not too much of a big deal. Alright, so what we're going to do is, let's think about this, alright? So let's say I'm finding the distance that the car traveled. Well, I can go second by second. So from 0 to 1 seconds, right, I'm going to go, the car goes from 20 to 30 miles per hour. So it starts at 20, ends up at 30, and if I'm going to do an underestimation, the one thing I know for sure is that 20 was the minimum speed. So I know for sure that the car traveled 20 feet. Alright, now from 1 to 2 seconds, again, minimum, I know it traveled at least 30 feet. And from 2 to 3, 38. And from 3 to 4 seconds, 44. And from 4 to 5 seconds, ending at 5 seconds, the minimum traveled was 48. This is 180. Alright, so I know that it traveled at least 180 feet. Now here, this is an underestimation. Alright, now before we go and on to the next part, looking at our overestimation, let's kind of dissect this a little bit. Alright, I'm going to draw a graph of the data. And it's just got to be a sketch, so I don't have to worry about being too accurate. Just gives me something to work with. That one's a little low. And that one's a little high. Alright, so there's some data. It'll work. Alright, now this is at an increasing speed, and so my graph looks like that. Force the dots on the line. Alright. Now, from 0 to 1 second, so this is my information on my graph from 0 to 1 seconds, between 0 and 1 right here. Now that right there is my change in time. In this case, it's going to be 1. And if I were to write that, I would write delta t. Alright, and I'll write that a little bit later. But my change in time is 1. Now, if I'm going to go with my underestimation said that I traveled 20 miles, or 20 feet per second minimum. So if I write that all the way across, going like that, and then I box it in with my 1 second, it creates a beautiful rectangle. And in this rectangle I can find the area of, and it happens to be length times width, but it happens to be 20 times 1. It's no coincidence that that area of that rectangle is the same as that number right there. Alright, now let's look from 1 to 2. 1 to 2, I said that they traveled a minimum of 30 feet. So if I go across 30 feet, I can make another rectangle. Find the area of that, and it turns out it's 30 times 1, which, no coincidence, the same as that number there. And I'm going to follow this method all the way across the rectangles. Oops, 38. And one more. And so the area underneath of this curve is representation of the distance traveled. Now it is, and here you can see, an underestimation. Exactly why? Because all of these little triangles right here, these triangle shapes, they weren't accounted for in my area because I was just estimating. And again, this is why it's an underestimation, because the area of all those rectangles is less than the actual area under the curve. Alright, so what else can we do to maybe look at it another way? We can look at an overestimation. Alright, in an overestimation, we're going to make our rectangles do the same thing, except for we're going to make it go over the function, so I know that it's more. Okay, so if I do my area under the curve, this time I know my distance is going to be this rectangle. Okay, I know these are the sides of my rectangle. Sometimes I get a little confused when I'm doing this, and so I know it's going to be the sides of my rectangle. So if I want it to be under, I would close it off here. If I want it to be over, I'll close it off on top of it. All right, and the area that would be 30 times 1. All right, so I got 30 for my first amount. That would be the overestimation of the distance traveled in 1 second. And again, if I look at my numbers, 30 is my greater number, so I know at most 30 and everything else will be below. All right, next one. And 38 times 1, so my next amount would be 38. And you can kind of notice it's going to follow the same pattern as above. And one more rectangle. Blue. $50. Alright, if you add that up, you're going to get 210. So at that point, this is going to be an overestimation because I use the maximum velocity each time. Well, logic would tell me then if this is that my distance traveled is more than 180 but yet smaller than 280, one thing I could do is I could average these two, and then I could maybe get a little closer to the actual distance traveled. But when we're starting out, a lot of times that's all we're going to do is estimate. And sometimes when they don't give you a function, you just get discrete data like this, then you're going to have to just do an estimation. So my average will be 210 plus 180 divided by 2, which is 390, which is 195. Make sure you label, feet, feet, feet. Alright, so if they ask you for an estimation, you're going to do this type, where your rectangle is below, and if you do ask for an over, your rectangle will be above, and if they ask for an average of those two, you add them and divide by 2. Alright, now, here you can see why this is an overestimation, because this little rectangles are more, those little triangle length thingies, are more than the actual graph. So ideally, what we're going to do to get a more accurate estimation of the distance would be to try to decrease that highlighted yellow area. Either we could shrink the top or we could make the bottom grow. Now, these will actually get smaller if I increase the number of rectangles that are drawn. So I'm only going to do this one right here, but in a lot of your homework they'll say, do this problem with 5 rectangles. Then they'll say, now do it with 10, and then do it with 20. And they want you to see how your answers are getting closer and closer and closer. Ideally, what we're going to do is we're going to make those rectangles go to an infinite amount using our calculus. Alright, but this is just an intro, so this is where we're starting. Alright, now, sometimes they call this, well not all, sometimes but always, but this is called a left-sided sum. Now the reason why it's called a left-sided sum is because the height of each rectangle that you're doing lands on your function on the left side. Right? Let's look at this red one right here. So if I look at that one, I've got the right side of this rectangle and I've got the left side of this rectangle. On the right side, the height out here is in the middle of nowhere. But on the left side, it lands right on this data point that I have on my function. So all of these do the same thing. The left sides touch the graph. So that's why it's called a left-sided sum. Now just note, all left-sided sums are not underestimations. They might be under, they might be over. It all depends on your graph. Because whether you're going concave up or concave down, or if you're increasing or decreasing, all those things can affect the data that you pull out of your graph. Now, similarly, notice how these rectangles all land on the right side. So, boom, right side. Red one, right side. Middle one, right. So this is what we call a right-sided sum. Again, it doesn't mean that it's over. It could be over or under. Alright, so what we're going to do with this is, In your homework, you're going to have similar problems. Make sure you draw pictures. I would suggest making 2 pictures when you're beginning your book, and a lot of your instructors will do the same graph on top of each other. But if you don't know what you're looking for, it's kind of confusing. So maybe make 2 graphs like I did here in this example, at least while you're starting out. Alright, now, what I want to do from here, though, is push you a little bit farther. What if I want to do this kind of situation on any function, any graph, any number of rectangles? So let's go ahead and build a formula. Now, left and right-sided sums have a name. They are called Riemann sums. And we can build those by doing a formula. And we're going to build the formula, so hopefully it makes more sense. Okay, so remember how I calculated these? I have to go like this, I guess, because I got to do 2. There's 2 formulas. There's going to be one for the left-sided sum and one for the right-sided sum. So my where'd that come from? My left is going to be, alright, now let's look how we built it. This was the area of the rectangle. Alright, so if I go over here, I got that by going left, width and height, width times height. Now my width is this distance here. Yes, it is 1. In fact, all of these widths are 1. All these widths should be the same. But how I want to calculate that is not just say in 1 second, because it might be different for a different problem. So I'm going to talk about this width right here as delta t. That just tells me the difference in your 2 times. So in this case, 1. Alright, now my height. Every time I multiplied my height, turns out, like if I use a 0 and if I could plug it into my function, when I put it into my function, I would get a value right here, which happens to be on your function there. So this value can be written as an f of x notation. Right, so f of x. Now I'm going to have lots of x's. I got 0, 1, 2, 3, however high I go up. So I'm going to go x sub 0 to distinguish this first as my initial x. And there's my second, my third, my fourth, so on, so on. So this right here represents this 20. Alright, now let's do the 30. I'm going to do the width, which is delta t, times the height. Okay, in this case, it's my f of x notation, and I'm going to be using this 1 right here, so it's 1 to the right of my initial point. So I'm going to write f of x sub 1. And I can continue in this fashion for all of my rectangles just by moving my x's over every time, because every delta t is my width, and all my heights are these functions. And this one's going to be at 0, this one would be at 1, this one would be at 2. And in this problem, I've got 2 more to go. But I'm writing a formula for everybody and every problem. So I am going to go plus dot 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 plus, and still doing my last one. So my width would be delta t, and my height is going to be f of x. Now, which x? Well, if I don't know, I usually just put it in a variable. But here, I want to kind of use a trick, because my last number is 5. But remember, I didn't use 5 in this one because it's out here in the middle of nowhere. I used just 4 and stopped there. So every time I'm doing a left-handed sum, I don't go to my last number that they give me in my data, so I don't go to that one. I'm going to go to the one before it. So I'm going to do x n minus 1, like that. Alright, now, that's annoying to write over and over and over. So there's another form that we use, and it's using your summation notation. Alright, so all of these have a delta t in them, so I write delta t. And then all of these have an f of x. But notice the x subscript is changing. So I'm going to put a little I right there. That I is going to be my number that changes in my summations. And in this case, I want my I to start here at 0, and I want it to finish at n minus 1. So these are telling me where to start and where to finish. And it looks kind of crazy, but if it doesn't scare you, then you look really smart if you can use it. Okay, now that's for the left-sided sum. Let's go ahead and do the same thing for the right-sided sum. And it's the same format. So for my right, I've got delta t, f of, now I don't want to do x sub 0, because remember on the right-handed notation, I didn't use 0 first. I used 1 because it's my right side in this red rectangle right here. that's my height that I want. So I'm going to start out at x sub 1. That gives me my area of my first rectangle. Alright, now let's move on to that one, the blue one next to it. Delta t, that's your width, and your height will be your function evaluated at 2. So, formula-wise, I'm going to go the next x over and do 2. And again, we continue in this fashion until we get to our last number, which in this case, now notice I did use 5. Remember when we calculated this 50 right here? It's going to be the area of this, which happens to be your right value right there. And in order to get that value on that function, you must put 5 in. So this one does go to n. Okay, now if I write it in this format, my summation notation, it's going to be exactly the same, except for this time, let's start at 1 and end at n. And there you have your Riemann sum formulas, your left-sided one and your right-sided one. Okay, little side note, I threw the delta t at you. However, delta t can sometimes be elusive, so we have a formula for that too. We always find how big our width is by taking our first number and our last number and subtracting them, and then dividing by how many rectangles we want. So in this case, I'd go 5 minus 0 divided by 5, and that's how I get 1. Formula-wise, this last number that we always use, we use a b, and the first number is an a, and then n is going to be equal to the number of rectangles. Okay, so there you go. That might come in handy later. Alright, so go ahead and try your homework. Your homework is like this. They want you to do 10 rectangles for most of your homework, or all of it, I'm not sure. But if you have any problems, highlight it and get back to me. Try to do at least the first one, and then we'll work on those other ones tomorrow in class if you're having problems. Alright, see ya.